This study is on the evaluation of the lightning image sensor by means of VHF ground-based lightning location systems as a reference for the upcoming MTG lightning imager. This study is part of the MTG-LI CalVal ongoing activities. It has been developed by the Lightning Research Group from the Technical University of Catalonia with the guidance of EUMETSAT. Authors are Nicolau Pineda, Joan Montañá, Óscar van der Velde, Jesús López and Bartolomeo Vitice. I am Nicolau Pineda from the Met Service of Catalonia. As a Met Service, we are very interested on the lightning information the next Meteosat generation will bring. In this regard, it is important to understand the difference with the current lightning data coming from ground-based lightning location systems. The present study focuses on the comparison between measurements made from the ISS-LIS sensor and a ground-based lightning location system, in this case a LMA. Like the global lightning mapper aboard the GOES-R series covering the Americas, the lightning imager on board of the next MTG will provide lightning optical observations for the whole Europe and Africa continent. This optical sensor will provide complementary observations to the existing ground lightning location system. EUMETSAT is preparing a CalVal program for the MTG-LI. Pre-launch activities include studies using proxy data, like the present one. Scope of the presentation. The in-orbit verification of the detection efficiency and accuracy of the LI will be a major challenge. To this end, EUMETSAT is developing CalVal activities. The LIS sensor on board of the International Space Station brings the opportunity to work with data resembling the future LI data, since the LIS is also an optical sensor working in the same optical frequency. Facing the forthcoming launch of the MTG, the LIS creates a unique opportunity to provide proxy data to help prepare research and operational applications for the upcoming lightning imager, like with the GOES GLM. Since the LIS has a similar detection principle, it can mimic to some extent what will be the LI data. To compare with, the lightning mapping systems are the best ground-based systems available. However, the comparison is not straightforward, as ground-based electromagnetic sensors see different lightning processes compared to optical systems, like the LIS. Lightning detection. Ground-based networks electromagnetic sensors see different lightning processes, depending on the operational frequency. For example, VHF-LF systems sees charge transfers over distance and time, mainly what is the lightning return stroke. Contrarily, on the left, we can see that VHF systems sees breakdown-related processes from the lightning channel. In contrast, optical sensors observe thunderstorms from above, and therefore lower channels like the step-out leader or the return stroke are frequently hindered by the optical thickness of the cloud. So the energy reaching the cloud top is influenced by the cloud optical depth, the vertical gradient of scattering, and the lightning channel height. The lightning image sensor, LIS, is a space-based lightning sensor aboard the International Space Station. The LIS instrument records the time of occurrence of a lightning event, measures the radiant energy, and estimates the location during both day and night conditions. The spatial resolution is of 4 kilometers at nadir and 8 kilometers in the borders of the swath. The operational optical wavelength of the LIS is 777.4 nanometers. The ISS-LIS data is retrieved from the space-time domain search. Here you have a link to the website. The period we selected corresponds to March 2017 to October 2018. On the ground side, the LMA system locates radio emissions in the very high frequency, in 3 dimensions, using time of arrival techniques with at least 5 stations. Each station samples the maximum RF power signal and amplitude, and with a GPS-derived precise time over 86 milliseconds intervals, it can locate the sources from lightning channels. So we are using the lightning mapping array deployed in the Ebro Delta region. The lightning mapping array system we are using in this study was deployed in the area of the Ebro River Delta in northeastern of Spain. Here in the left you can see the station distribution, and in the right an example of one of the stations that measures impulsive radiation events in the VHF band. This is an animation of one detection. In this slide you can see an animation of one flash as detected by the LMA. The located sources are mainly coming from negative leaders moving through regions of positively charged cloud particles. The LMA also detects weaker sources coming from positive leaders, which moves in the negative charge region. So what is really a lightning flash? This may seem a trivial question, but for each system a lightning flash is something different. From the VLF and LF systems, a lightning flash is basically a sequence of resting strokes. However, for a VHF system, a lightning flash is the channels that spread through the cloud. And finally, for the optical system, a lightning flash is the energy that reaches the top of the cloud. So what is a lightning flash for the LIS? Here we can see an example of the LIS detection grid. An event is what the instrument measures, a triggered pixel in a detector grid. These events are then grouped. A group is a collection of adjacent triggered events occurring in the same integration period, 1 millisecond. And the groups aim to represent a lightning stroke occurring in nature. Finally, the flash is formed by one or more groups that occur within 330 milliseconds and 60.5 kilometers of separation, which aims to represent a geophysical flash. So to allow comparison between systems, we are using the LIS grid. Here in the right you can see an example with different events grouped in two groups and in one flash. And above we are representing what has been seen by the LMA. The dataset is made of 8 episodes with around 300 LMA LIS concurrent measurements. These are two examples on the 18 September 18 and 18 October 8. So you can see on the top the LMA detections and the concurrent LIS detections on the lower panels. For the concurrent measurements on the 18 October 18, on the lower panel you can see that black circles correspond to the LMA sources that have occurred in time and location within the field of view of the LIS, whereas the green ones occur already outside the field of view of the LIS. You have to keep in mind that the LIS passes above the area at around of 2 seconds. So each vertical line of sources corresponds to a lightning flash, and the corresponding LIS events are plotted on the bottom as blue asterisks. We can see that sometimes the LMA flash has no LIS correspondence, so this flash is not detected by the LIS. This is an example of a flash-by-flash comparison. This multi-panel displays an intercloud as detected by the LMA and the events detected by the LIS. The top panel is the altitude above the mean sea level versus the time in seconds. So you can see how the lightning propagates from left to right, and the corresponding LIS detections that are arbitrarily plotted at 0.5 kilometers. On the bottom, the left panel is a plane view, so you can see the longitude and latitude of the detection. Finally, the panels on the right show the altitude versus longitude, so a south-north view, and with longitude, so a west-east view. This is another example of a flash as seen by both systems. You can see how the LMA channel propagates and all the corresponding LIS detections which are more scattered around. On this example we can see two different flashes, one near the LMA region and one farther away. The first flash is well detected by the LMA and the LIS. However, the first flash is well detected by the LMA. Contrarily, the second one is already farther away and it shows few sources from LMA. Finally, this is an example of 4 flashes detected by the LMA, and only the first one was detected by the LIS. You can see that only concurrent black events correspond to the first flash. Flash number 2 and number 3 are low and in altitude, so presumably the optical depth hinders these flashes from the LIS. Finally, in this example, sources are colored by power and not by time. So it is to show that concurrent LIS events occur at the beginning of the LMA flash and appear to be related to the height of the sources or even to the intensity of the negative leader. Contrarily, the following positive leaders at lower altitudes in the second half of the flash have no LIS detections. Results. We are going to present results on detection efficiency, location accuracy, flash duration, events per flash, and LIS events compared to LMA sources, height and power. So regarding the flash detection efficiency, the flash detection efficiency has been calculated as the ratio between the flashes detected by the LIS and the flashes detected by the LMA, which are taken as ground truth. Detection efficiency has been calculated in a restricted area, so it's 150 kilometers around the network to ensure that all flashes are detected properly by the LMA. Considering the LMA range of 150 kilometers and a time tolerance of plus minus 0.1 second, and considering also that each flash has to have at least one LIS event, we finally have 272 LMA flashes and 185 LIS flashes. So allowing a distance between centroids of both flashes of a maximum of 50 kilometers, we finally have a flash detection efficiency of 68%. The flash detection efficiency has a relation with the LMA channel height. Here in the right panel we can see that the detection efficiency drops with the altitude of the LMA detections. So there is an effect of the optical depth of the cloud that hinders lower detections. To calculate the location accuracy of the LIS flashes and taking the LMA as ground truth, we have calculated the offset of the flash location between centers. Here in the left you can see an example of a concurrent LMA flash in both systems. The blue squares correspond to the LMA detections and the red circles to the LIS detection. So in the right, frequencies represent the average offset between both flashes. This offset has an average of 4.8 kilometers and a median of 2.1 kilometers. Another way to estimate the location accuracy is through the spatial overlap. So here in the left you can see an example of how a lining detected by the two systems overlap. In this example, 55% of the LMA is detected by LIS, and 29% of the LIS is not matched by the LMA detection. So the overall overlap average for the whole study is 47%. Finally, lining extension can be estimated also through the sum of pixels corresponding to both systems. And we obtain LMA flashes are, on average, 200 square kilometers, while the LIS events are a little bit larger. Flash duration is calculated as the difference between the first and the last source. This has been done for both systems. In this example, we can see that the LIS flash duration is shorter. This happens with the majority of flashes. So for the whole study, the average duration for the LIS flashes is 0.69 seconds, while for the LMA it's 0.86 seconds. Shorter flashes last for just a tenth of a second, while the longest ones has a duration above 2 seconds. Here we compare the flashes detected by both systems. We can see that normally one LMA flash corresponds to one LIS flash, but sometimes one LMA flash contains more than one LIS flash. So 60% of the LMA flashes have one LIS flash above about 20% of the LMA flashes has 2 LIS flashes, and the other 20% has 3 flashes or more. Finally, we have also compared LIS events with LMA sources. This equivalence has made with a time difference less than 10 milliseconds and a distance below 10 kilometers. This way, we can estimate the height of the LIS detections. The box plot on the left shows that the ISS-LIS events that match with the LMA source are slightly at higher altitudes compared to all LMA population. Regarding power, in the right, we also can see that LIS events that matches LMA sources has a stronger power than all LMA population. Summary: lightning mapping arrays. Lightning mapping arrays provide the most comprehensive picture of the lightning channel propagation inside the cloud. Typically, LMA provide 100 to 1,000 sources per lightning flash. These detections allow the discrimination of the lightning leader polarity and also the identification of the thundercloud charge regions. LMA systems are also easy to set up for campaigns, like the one we did in Switzerland in the summer of 2017. On the contrary, LMA systems are of limited range, typically 100 to 150 kilometers radius from the center of the network. They also provide a large amount of data to be processed in real time, and this can be a problem, also for storage. Finally, lightning return strokes processes are not detected by the LMA. So normally, we have to complement this data with VLF or LF lightning data. Regarding the LIS flash detection efficiency, results show that it's around 70%, but that it's episode sensitive and can vary from 50 to 90%. We also have seen that detection efficiency drops to 20% when lightning flashes occur below the 75% of altitude for a given episode. We think that this is due to the cloud optical depth and particle scattering of the thundercloud. Regarding location accuracy, the average offset between the IS flashes and LMA flashes is of 4.8 kilometers, and the pixel overlap is of 47%. Regarding the flash area, we have seen that LIS flashes typically are larger than LMA and are around 200 square kilometers. Finally, regarding flash duration, we have seen the average duration for the LIS flash is of 0.7 seconds, a little bit larger in LMA flashes. Regarding the source pair comparisons, we have seen that sources at higher altitudes are better detected by the LIS. Instead, there is no apparent relation between the LIS radiation and the LMA power. We think that these detections correspond to different processes. Finally, you can find the whole report in the following address. Thanks for listening.